This is Physics 1060, Lecture 9. Today we're going to talk about the origin of the solar system as a whole. Now, a major goal of our study of the solar system is to understand its formation. We do not have a complete understanding of what happened yet. What we're going to get is a mixture of firm theory with some speculation. Among the simple clues we have gained so far are a uniform rotation of the solar system objects. Meteorites are about 4.6 billion years old. There are more impact craters 3 to 4 billion years ago than there are now. Some terrestrial planets have iron cores. Comets are icy. Asteroids are rocky. Jovian planets have much more hydrogen and helium than terrestrial planets. All objects in the solar system seem to have formed at nearly the same time out of the same original cloud of gas and dust. And radioactive dating of rocks from the Earth, from the Moon, and asteroids suggest an age of about 4.5 billion years. Now, that's not the only way that we gauge the age of the solar system. Science likes to have many different measurements that all point to the same thing, and there are many different things. For example, we can focus on the sun and look at current observation and nuclear reaction rates, and we get a very similar age. A theory of the solar system's formation must account for the following. Planets orbit in the same direction and in the same plane. Rocky inner planets are gaseous, liquid, icy outer planets. Compositional trends in the solar system. All solar system bodies appear to be less than 4.5 billion years old. And there's lots of other details, such as the structure of asteroids, the cratering of planetary surfaces, detailed chemical composition of surface rocks and atmospheres, etc. All these things have to fit into one package. And that brings us to the solar nebula hypothesis. It is derived from the 18th century ideas of Laplace and Kant. They proposed that the solar system evolved from a rotating flattened disk of gas and dust, which we call an interstellar cloud. The outer part of the disk became the planets, and the inner part became the sun. Now, this hypothesis naturally explains the solar system's flatness and the common direction of motion of the planets around the sun. Now, interstellar clouds are common between the stars in our galaxy, and this suggests that most stars have planets around them. Now, interstellar clouds come in many shapes and sizes. The one that formed the solar system was probably a few light years in diameter and 2 solar masses. Typical clouds out there are 71% hydrogen, 27% helium, and traces of other elements measured from spectroscopy. This is a Hubble Space Telescope picture of something called the gaseous pillars, and we see these orange objects inside these gaseous clouds that are actually new solar systems and new stars starting to form. Now, clouds also contain tiny dust particles called interstellar grains. The grain sizes from a few molecules to a few micrometers, and they're a mixture of silicates, iron, and carbon compounds, and water ice. So, in the beginning I have a large cloud, and it might be spinning ever so slightly. All it has to do is maybe this side's moving even a little faster than this. Now, this collapse can be triggered by collision with another cloud as they're moving through the galaxy, a nearby supernova, exploding star. The rotation forces the clouds to gravitationally collapse into a rotating disk. Since, again, if it's rotating at all, along the axis of rotation, it's very easy to go along the axis, but not towards the axis of rotation. So a few million years pass, and the cloud collapses into a rotating disk that has a bulge in the center, because if it's a spherical cloud and we compress it down, there's more material in the center than there are at the edges. So this disk might be about 200 astronomical units across, 10 AU thick, is called a solar nebula. And the bulge becomes the sun, and the disk condenses into planets. So the solar nebula, a large gas cloud, collapses down into something flat. The center becomes the sun, and the outer, as things start to form, start to take up all the material in there, and eventually the material gets collides into more and more objects, and you end up with only the planets as it sweeps out all the material in its orbit. Now before the planets formed, the inner part of the disk was hot, and that's generated by gas falling into the disk in a young sun. The outer disk is colder than the freezing point of water. Now, one of the reasons that we like this is we see other gas and dust disks in nearby clouds. Here in a cloud we see these accretion disks starting to form. In fact, if we look at nearby stars and we block out the light from them, we see a disk of material around it. Or here, looking at the disk more flat on, we see the gas and dust accretion disk as we look at some of the nearby stars. Now, condensation occurs when a gas cools below a critical temperature at a given gas pressure, and its molecules bind together to form as liquid or solid particles. We see this here as steam starts to form small water droplets, and actually if they cool down and maybe they strike something like a mirror, they'll start to form larger droplets. Now, iron vapor condenses at 1300 degrees, and silicates at about 1200 degrees. Of course, water vapor condenses at room temperature in air. In a mixture of gases, materials with the highest vaporization temperature condense first, and condensation ceases when the temperature never drops low enough. The Sun kept the inner solar nebula out to about Jupiter's orbit too hot for anything but iron and silicate materials to condense. The outer solar nebula was cold enough for ice to condense. The next step is for the tiny particles to stick together, perhaps by electrical forces, into bigger pieces in a process called accretion. As long as the collisions are not too violent, accretion leads to objects called planetesimals, ranging in size from millimeters to kilometers. Planetesimals in the inner solar nebula are rocky iron composites, while the planetesimals in the outer solar nebula are iron rocky icy composites. Planets formed from gentle collisions of the planetesimals, which dominated over the more violent shattering collisions. Simulations show that planetesimal collisions gradually lead to approximately circular planetary orbits. As planetesimals grew in size and mass, their increased gravitational traction helped them to grow faster into clumps and rings surrounding the Sun. Planet growth is especially fast in the outer solar nebula due to the larger volume of material to draw upon, and larger objects, bigger than Earth, could start gravitationally capturing hydrogen and helium gas. So, solar radiation heats up the inner solar system. There's no ice condensing in here or water, only the rocky stuff. Water-ice particles are in the outer part. So in the center we get iron and silicate-rich planetesimals. In the outer we get icy-rich planetesimals. And then in the center we get the planetesimals forming together and creating planets. In the outer systems they're large enough that they'll gather and capture the helium and hydrogen to make the gas giants. We have continued planetesimal bombardment, and internal radioactivity melted the planets and led to the density differentiation of the planetary interiors. The moons of the outer planets were probably formed from planetesimals orbiting the growing planets. They're not large enough to capture helium or hydrogen. The outer moons are mainly rock and ice, giving them solid surfaces. The rain of planetesimals cratered the surface. The remaining planetesimals became small moons, comets, and asteroids. Atmospheres were the last planet-forming process. Outer planets gravitationally captured their atmosphere from the solar nebula. Inner planets created their atmosphere by volcanic activity, perhaps from comets or asteroids that vaporized on impact. Objects like the Mercury and the Moon are too small, meaning not enough gravity to retain any gas on their surfaces. That's our best guess on how the solar system formed. We would be open to a new theory, but this one does describe all the observations in our solar system. What we need to test our theory is to see it happen. And while we can't go back in time to see it, we can look for it happening in other gas clouds in our solar system. So we look for extrasolar planets. Now, evidence exists for planets in other nearby stars. The new planets are not observed directly until very recently. One method for looking at them is their gravitational effects on their parent stars. And the ones that we first started seeing were a surprise because they're huge planets very close to their parent stars. So the idea is that the huge planets formed far from their stars, as the current theory would project, but their orbits subsequently shrank. This migration of planets may be caused by interactions between the forming planets and leftover gas and dust in the disk. Here's the Epsilon Andromeda system. Shows some planets that have very large sizes, like on the order of Jupiter bigger, actually inside the orbit of Venus and Earth, and some closer than Jupiter is. In fact, if we look at all the first ones we started to see, we see some very large stars that are closer than the Earth is. So do these observed extrasolar systems disprove our model of our solar system? No. We cannot see many systems yet. The systems with large close planets are just the ones that are easiest to find. That doesn't mean they're the most common, just the easiest to see. This is actually an area that there's a lot of work going on currently. Now, more recently, the Hubble Space Telescope has observed planets actually in transit by looking at the light intensity of a star. And we see the light intensity of a star, every once in a while we see a dip. Well, this is a planetary system that actually the plane of the planets is pointing right at the Earth. And we can see how fast the planet's moving across the star and how big it is by the duration and the dip in light intensity from the star. By looking at the spectra, then, we can determine the composition of the atmosphere. Current estimates are that 10 to 20% of stars have planets that may be habitable or Earth-like. In other words, they have planets that have the right composition and the right distance from the sun to have liquid water on their surface. Now you can help. There's a website called Zooniverse that has many different science projects that all they need is someone to look at something and make a decision. Do they see something here or there? And one of them is you helping find planets around the stars. If you're interested, go to the website listed here and take a look at finding planets around stars. And that's it for this chapter.